Introduction to Vibration Measurement, Fundamentals and Techniques for Detecting Mechanical Vibrations. Importance and Applications, Overview of Vibration Measurement. Vibration measurement is a critical aspect of predictive maintenance and condition monitoring in industrial environments. It helps identify mechanical issues such as imbalance, misalignment, and bearing defects before they lead to catastrophic failures. By understanding vibration characteristics, engineers can optimize machine performance, reduce downtime, and extend equipment life. Applications span across manufacturing plants, power generation, automotive, aerospace, and even consumer electronics. Accurate vibration measurement ensures compliance with safety standards and enhances operational efficiency. The process involves capturing dynamic motion data and interpreting it to diagnose machine health, making it an indispensable tool for reliability engineers and maintenance teams. Vibration sensors and units, displacement, velocity, and acceleration. Vibration sensors measure motion in terms of displacement, velocity, or acceleration, each serving different diagnostic purposes. Displacement sensors, often proximity probes, measure the relative movement between a shaft and its bearing, ideal for low-frequency vibrations in large rotating machinery. Velocity sensors, typically electrodynamic, measure the rate of change of displacement and are widely used for general machine monitoring because they correlate well with energy levels. Accelerometers measure acceleration and are suitable for high-frequency vibration analysis, such as detecting bearing faults. Understanding these units and their applications is crucial for selecting the right sensor for specific machinery and fault detection scenarios. Where and how to mount sensors. Proper sensor mounting is essential for accurate vibration data. Sensors should be mounted on rigid surfaces close to the source of vibration, such as bearing housings or machine casings. Common mounting methods include stud mounting, adhesive mounting, and magnetic bases. Stud mounting provides the most reliable readings by ensuring firm contact, while adhesive and magnetic mounts offer flexibility for temporary measurements. The mounting location should minimize resonance and avoid structural weaknesses. Incorrect mounting can introduce errors like signal distortion or attenuation, leading to poor diagnostics. Therefore, following manufacturer guidelines and ensuring clean, flat surfaces are critical for repeatable and high-quality measurements. Standard practices for identification, naming conventions. Consistent naming conventions are vital for organizing vibration data and ensuring clarity in analysis. Each measurement point should have a unique identifier that includes machine name, component, and axis orientation. For example, a pump bearing might be labeled as Pump 1 DE-H, where DE stands for drive end and H for horizontal axis. Standardized naming reduces confusion, facilitates route creation, and improves communication among maintenance teams. It also supports automated data collection systems and trend analysis by maintaining uniformity across databases. Adopting industry standards or company-specific guidelines ensures that vibration data remains traceable and interpretable over time. Ensuring reliable measurements, repeatability, and quality. Repeatability refers to the ability to obtain consistent vibration readings under the same conditions. High-quality measurements depend on factors such as sensor calibration, proper mounting, and stable machine operating conditions. Variations in speed, load, or environmental factors can affect readings, so measurements should be taken under similar circumstances for trend analysis. Using calibrated instruments and following standardized procedures enhances data reliability. Quality checks, such as verifying signal integrity and avoiding interference, are essential to prevent misinterpretation. Reliable data forms the foundation for accurate diagnostics and predictive maintenance strategies. Understanding vertical or V, horizontal or H, axial or A, radial or R, and tangential or T. Vibration measurements are typically taken along multiple axes to capture the full dynamic behavior of machinery. The common axes include vertical or V, horizontal or H, and axial or A, which correspond to directions relative to the shaft. Radial or R and tangential or T axes are used in specialized applications for rotating components. Measuring along these axes helps identify issues like imbalance, misalignment, and looseness, which may manifest differently depending on direction. Comprehensive analysis requires data from all relevant axes to ensure accurate fault diagnosis and prevent overlooking critical vibration patterns. Routes in vibration measurement, definition and creation. A route in vibration measurement refers to a predefined sequence of measurement points across multiple machines or components. Routes streamline data collection by guiding technicians through a systematic process, ensuring all critical points are monitored regularly. Creating a route involves identifying key assets, defining measurement locations, and organizing them in a logical order for efficient data acquisition. Routes can be managed using software tools that automate scheduling and data logging. Proper route planning improves consistency, reduces missed measurements, and supports trend analysis for predictive maintenance. Common issues and best practices, detecting and avoiding poor data. Poor data can result from incorrect sensor mounting, environmental interference, or operator error. Common indicators include erratic readings, unexpected spikes, or inconsistent trends. To avoid poor data, ensure sensors are properly mounted on clean, flat surfaces, verify calibration, and maintain stable operating conditions during measurement. Regular training for technicians and adherence to standardized procedures further reduce errors. Implementing quality checks, such as reviewing signal coherence and validating against historical data, helps detect anomalies early. Reliable data is essential for accurate diagnostics and effective maintenance planning. Let's summarize and key takeaways. Understanding vibration measurement principles is fundamental for maintaining machinery health and operational efficiency. From selecting appropriate sensors and mounting techniques to following naming conventions and ensuring data quality, each step plays a vital role in accurate diagnostics. Incorporating multi-axis measurements, structured routes, and robust quality checks enhances reliability and supports predictive maintenance strategies. By mastering these concepts, organizations can minimize downtime, reduce costs, and extend equipment life.